All right, hello friends, it's Mr. Who here, back with some more pre-calculus. Okay, so today we're going to be following up on the last lesson. Okay, that was about kind of multiplicity of zeros and polynomial functions in the plane. We're going to keep going with this idea of polynomial functions. Okay, fn's being function, of course, and we're going to explore some terms we use to describe them, such as degree, which we kind of already talked about, but kind of formalize it with the notation rather than the graphs this time. And then we'll also talk a bit about how to simplify again, as well as how to actually, use those zeros to get your polynomial into standard form, as well as what standard form even is. So let's go ahead and get into it. So first of all, when we talk about polynomials, okay, we should know that there's a standard form for these guys. Okay, a standard form for a polynomial function is something that looks like this, where you have an ax to the n plus, well, a sub n, we should say, a sub n x to the n plus a sub n minus 1 to the times x to the n minus 1, and so on and so forth, until we have a to the 1, x to the 1, okay, plus a to the 0. Okay, and that is our standard polynomial form. Typically, we have a function here as well, f of x. Okay, so when we talk about standard polynomial form, or general form, as it could be also called, standard, let me actually erase this first part, standard general form, okay, okay. That means we're talking about polynomial with degree n, okay, which can be any number, right? And it's in the form where you have the highest degree first and the constant last. There's no x at the very end there, it's just the constant. Okay. So speaking of those, let's just go ahead and label these here as well. Degree n, so the nth term, okay, should always come first. Okay. And in addition to that, okay, this guy right here, okay, a sub n, is the leading coefficient. Okay. This is probably not news to you, so we talk about this all the time. Okay, leading coefficient. So if you remember that still, you're in a perfectly good spot to stay up with it. Now these middle terms aren't very important to us. We don't really need them for anything in terms of identifying what the polynomial is, but we do have some importance with this one. Okay, this is our constant term. Okay, it's also our y-intercept. So if you're looking on a graph, our a sub 0, whatever number that is, will be where we intersect at the y-axis. So those are just a couple terms kind of surrounding polynomial functions. You can tell the degree based off of what the highest degree is there. Okay, and if you happen to have multiple variables, you just add up all the exponents together, and that's your degree. So um, in pre-calculus anyway, we usually deal with just one variable, but at least in the DeltaMath modules, you will probably have to think about talking about multiple variables. So that'll just be a bit of review from earlier. All right. Okay, so now that we discussed what exactly a polynomial function is, let me go ahead and take all of these guys and just erase all of them for you. Actually, hang on. Take all these guys and delete. All right, nice and simple. Okay. Let's continue on. Whoops, I'll read that. As you can see, I'm not very used to this right now, but I'm trying some new stuff. Okay, now let's talk about simplifying polynomials. Okay, simplifying polynomials. Now, when we talk about polynomials and simplifying them, I'm talking about starting with factors and multiplying them out. So for example, you have x plus 2 times x minus 3. Of course, you know to FOIL, right? That's something we've been taught before. You FOIL by taking the first and multiplying by the first for an x squared. Take the first out of the outer ones, x and minus 3, so minus 3x, plus 2x, minus 6. Now, why are we going over this again? Mostly because we're going to be making polynomials and then trying to uh, simplify them to standard form. And not as simple as this, right? This is stuff we already know how to do. You just add up the like terms and you just have minus 3x plus 2x is minus 1x minus 6. Okay, easy peasy stuff, right? So let me erase all that. Okay. Let me give you something a little harder to think about. Okay. Give you something a little harder to think about. Something like 2x plus 4 times x squared minus 3x plus 7. Okay. Just kind of a generic binomial times a trinomial. Now with this one, you are still going to be foiling. Okay. But when you foil with these ones, you have to make sure you hit all of the terms. You have to distribute all the way. So one method you could use to do this better, okay, and keep track of it is to kind of make a table, okay, where it will list all the terms for you. So on the side here, I have 2x and 4. So on the top, I'm going to have x squared minus 3x and 7. And so I'm just going to multiply them across in the cross sections. So x squared times 2x, that's 2x cubed. X squared times 4, 4x squared, okay, so on and so forth. So this will be minus 6x squared, 12x minus, and then we have 14x and 28. Okay. When all is said and done, okay, the table should at least, have this kind of pattern where your like terms end up in boxes like this. Okay. So you can kind of see where they should add up. You can kind of do that math while you're still on the table. Okay. In the end, I should end up here with a 2x cubed, oops, 2x, that's what I want, minus 2x squared plus 2x plus 28. That's my fully simplified in standard form polynomial expression. Okay. So of course this technique can also be applied to 3 by 3, a trinomial times a trinomial, and you'll probably have to do that a couple times in the DeltaMath. Okay, so make sure you guys know how you're dealing with this, okay, as well as what to do when you have multiple binomials multiplied by each other. It's kind of like the same deal. You just multiply one at a time and then go on forth down the kind of run on that one. Okay, now the next step here, I'm going to go ahead and select and clear all this again. Looks like I missed a couple. Whoops, that's not what I wanted to do. Okay. For the next couple, I just want to talk about zeros a little more. Okay, so let's say, for example, you've got a graph here. Okay, ooh, very bad graph. I'll use the line tool. How's that? I'll use the line tool. Let's say you have a graph, okay, in the plane, and looks something like this. Okay, so just a generic polynomial function, right? And I got points of my zeros right here, and right here. Well, we know these to be our roots. These are our zeros, right? We've already talked about them a little bit. But what's new to us today is that when we talk about our values, let's call this x1, x2, and x3, the places where these are zeros, okay, we're talking about a polynomial that is actually something like this. F of x equals x minus x1, x minus x2, and x minus x3. I can run out of space there, but I can put it in there. So what I'm saying here is that if you have a polynomial and it crosses 3 times, these are all multiplicity 1, by the way, you should have known from last time. It's a cubic polynomial, right? I have 3 binomial factors that make up that polynomial. And those binomial factors, in fact, are taking those zeros, okay, and putting them in here with the minus sign. We'll talk a little bit more about how to get these, okay, from our standard form. But for now, we're going to talk about getting to that standard form from a graph. So if we really wanted to get all this out, okay, you just multiply it all out, and you should end up with something with x cubed, and then a bunch of other stuff, right? Plus some constant a sub 0. Okay, so whatever these x1, x2, x3 zeros are, you can always get the simplified form by multiplying them all together. And we're going to take a look at the DeltaMath for a bit more guidance on that one. So I'll see you in the DeltaMath. All right, welcome back. So this is our DeltaMath module, right? Polynomial function from graph. Okay, now they want a lot of information, so it's up to me to help you guys figure out what information we need, right? Now, remember when I said the zeros kind of dictate how you're supposed to write the polynomial out? Okay. Let's go ahead and get our roots from our graph here. If you're looking at the graph, you should be able to see that right here and right here are my roots, my -1, okay, and my positive 2. So those are my two roots, but this is a cubic function, so I'm looking for three binomials here. Remember from the last lesson that this little dip might bounce off the x-axis means this is actually multiplicity 2, which means I should need to have two factors of that. So right now I'm looking at x plus 1, remember it's minus a negative, times x minus 2 times x minus 2 again. Okay. So that's what I'm looking at right now so far. Okay. We'll come back to that in a sec. Let's do the little multiplication to get this all out. X times x, x squared, negative 2x, plus x, minus 2. So that's my first group. I'm going to leave this other one out here. Do one at a time so you can save yourself some trouble. This is x squared minus x minus 2 times x minus 2. All right. Now, whatever method you choose to use, personally I prefer the box method, so let's do the box. There's my left side, and here's my x and minus 2. You'll get all your terms together. Okay, so x squared times x, that's x cubed, of course. Negative x squared minus 2x minus 2x squared plus 2x plus 4. So there's all my terms. Okay. Remember, add your like terms together, and I'll end up with something along the lines of x cubed minus 3x squared. Those actually cancel, so I won't have any at all, plus 4. Okay. Now, we're almost done here. There's a little bit of an issue, though. If you look at the graph, okay, it's very obvious that the y-intercept is right here. Okay, this is the y-intercept. Y-intercept is 0, 12. Okay, well, what I just got here, okay, my y-intercept is 4. Well, that's not right then, is it? We actually need to multiply this polynomial by a constant that would let us have this y-intercept of 12. If you thought of the number 3, you are totally right. So let me go back to drawing with the black here. We need to multiply this whole product by 3. Okay. So let me scroll down here and plug in the answer down here. Follow along. Looks like I've covered up my answer once more. Move this around. Okay, that's a little better. Okay. Now you can see my work out there. All right. So in the end, 3 times x cubed, that's my first term, minus 3 times 3 is 9, x squared, plus the 12. Okay. This should be our final polynomial form for this function from the graph. So let's see if I'm correct here. And yep, it looks like it. So if you are worried about having to keep all this information stuck together, okay, take it slow, figure out your roots, okay, put it all together for multiplication, figure out your y-intercept, try to align your y-intercept and your final product, okay, with a factor. You cannot add to do that. You have to use multiplication. And you should be able to get that answer. Okay. You can always refer to this video if you have trouble too. All right, let's continue on to the next module now, shall we? All right, now back with another example. This is one with a table, so it's a little different from the graph one, but it should be the same type of problem. So it's another way to get your feet wet at this kind of stuff. So again, we're looking for a cubic polynomial in standard form. That's what this problem wants us to find. And we are given a table of values. Now, what values are important in the table? It should be the zeros, the roots that I was talking about, and the y-intercepts. Let me find my zeros. Here's one of them with 2, 0. Another one with negative 1, 0. Finally, negative 4, 0 as my final root there. Then I also need a y-intercept, right? And that's with the 0 on the axis. So I'm going to mark that with a blue X. So those are my values of importance. Everything else doesn't really matter. They are, of course, points on the graph, but they're not very important to us unless there's like a vertex in there. But it's a cubic function, so no vertex to be found. So now, remember, we use these as our binomial components, x plus 4 from the negative 4, x plus 1 from the negative 1, and x minus 2 from our minus 2 down here. Okay. Now we just do some multiplication here, x plus 4 and x plus 1, x squared plus 4x plus 1x plus 5x, plus 4 times plus 1 is plus 4. And I still have that x minus 2 here. Now let's do a bit of a table here. So I got x squared, 5x, and 4 on the top. On the bottom, we got x and minus 2. It can be the other way around too. Doesn't really matter. My terms are x cubed, 5x squared, 4x, and negative 2x squared, negative 10x, negative 8. Okay, so there we go. There we have it. So we put these all together. X cubed should go out here. It's all alone. Plus 5 minus 2, that's plus 3 in total. X squared. And then I got a 4x and a minus 10x. The minus is overpowering it, so I got minus 6x. And finally, minus 8 is all by itself. Now we check to see if our y-intercepts match, and ta-da, indeed they do. Remember, if they didn't match, you'd have to multiply this whole polynomial by something to try and get it to match. You cannot add, you cannot subtract it. So since this is already kind of in the form, let's go ahead and just put it in and see how it fares in our little answer box. X cubed plus 3x squared minus 6x minus 8. Checking our answer here. Boom, big old check mark. So again, take your time on these. They are pretty difficult, a lot of room for error, and you know how DeltaMath likes to deal with errors. They like to give you no credit. So take your time, especially on the higher polynomial functions like quartic and cubic. Okay, there's a lot of room for mistakes there. So really make sure your math is rock solid. It'll probably give you a couple chances to, see if you can find your mistake. But I would say think it through on these problems so you don't have to do that. Okay. This has been Mr. Who talking about polynomial functions as well as finding their standard form from graph and table. I will catch you guys all next time, which should be something like division maybe. So we'll see you then.